Oh, not again. The battery's always flat and I don't have any spares. So annoying. There has to be an easier way. Hello, today I have a project build. I have this electronic caliper and every time I go to use it, the battery's flat. So I got sick of always having to get new cells and decided to take a crack at making a quick and easy rechargeable circuit so my digital calipers will work when I need them. There are hundreds of ways to make this work, so this is just one, and maybe not the best one by any means. In this video, I will analyze how much current the calipers need, design a circuit, deadbug assemble, and make it rechargeable. All this with parts I have on hand. No circuit boards here. I noticed the cells wouldn't last long in the calipers. I tried a few brands of batteries and fresh batteries and didn't see any improvement, so I started taking the cell out of the calipers in between every use. This helped a little, but the cells would still be flat, and it is also annoying trying to pry the tiny cell out every time. These are on the cheaper end of the scale for calipers, so maybe this is expected. The calipers use a 1.5 volt button cell battery. This particular variety is a silver oxide cell. These cells are supposed to have very stable output voltage, but do tend to suffer from more rapid self-discharge. Here we can see the battery datasheet, and it claims these batteries lasting about 5 years, but in general, I haven't seen more than 1 or 2 years out of these cells. I took a measurement of the cell that was in there, and it is thoroughly discharged. After doing a bit of research, I found that these cells tend to self-discharge a bit quicker than the claim, and they're also quite prone to physically leaking, so I decided this has to go. So I want to charge quickly, and have plenty of juice to run the calipers for a few days, and have the calipers still easy to use. I've heard of this thing called USB, and I think it can charge devices. So I have a problem, and I need to find a solution. The battery stores energy and delivers it to the calipers for operation in the most basic form. I need to first make a few measurements to determine how much power the calipers actually need during normal operation, then do some calculations to figure out how much energy is required, and finally I can do some component selection and circuit design to make everything work. Finish that off with a dash of awful assembly and then use it and never think about it ever again. As a preview, I will be using some of these super or ultra capacitors or double layer electrolytic capacitors that I've had laying around the shop for a while and thought maybe this would be a good, suitable replacement for a coin cell battery. The characteristics of a supercapacitor mean that they can be charged very quickly. The issue is the voltage is not delivered steadily to a circuit, so that will require some kind of regulator to make sure the voltage doesn't go too high or too low during various states of charge of the capacitor. They also don't wear out very quickly, so we can see from a datasheet on one of these, 1,000,000 charge and discharge cycles is great. That should be plenty for this application. I'm hoping this is a good project because there are no rechargeable coin cell batteries for this kind of application, or at least none that I could find. If anyone knows of any, please leave it down in the comments. So that's the plan. Make a replacement for the 1.5 volt coin cell battery for my calipers using a fast charging, long lasting supercapacitor and a simple control circuit, which also had some challenges along the way. Paraphrasing Dave from EEVblog, I hope you build your project and it doesn't work. To start, I need to get some measurements to determine the amount of current required to operate the calipers when powered off and when powered on. To do this, I have a setup that includes a DC power supply to mimic the coin cell battery, along with a current shunt to measure the current draw. This measurement box is called a microcurrent, and you can get into the nanoamp range while minimizing the voltage drop from the shunt inside the meter, causing incorrect readings or dropping the voltage to the device being tested. I thought I might have needed this to figure out the standby current draw when the calipers were off, but it turns out the current is way more than I anticipated. Otherwise, I could have just used the built-in feature on the multimeter, which is usually accurate enough as long as you set the voltage in the correct location after the current measurement. The voltage will also fluctuate at this point if you have significant voltage drop in the current shunt being used, so this can lead to instability that wouldn't necessarily be present with a battery. I didn't know it at the time, but I made an error when making these measurements that would cause me issues. I will explain more later in the video. The current draw, when off, was measuring around 16 microamps, and to my surprise, it was also around 16 microamps when turned on. So I guess this means the circuit is always drawing the same amount of power regardless of whether the screen is on or off. This starts to explain the less than stellar battery life I had noticed. I am not sure if this device has some kind of low power mode it enters at all, but in this particular unit, it doesn't seem to have it. I also checked where the low battery trip point was, so it would display a low battery warning on the display and it would flash on and off, which seems to be at 1.39 volts, which would represent a fully depleted silver oxide battery. There's a little hysteresis on this condition, which means that it trips the low battery warning at 1.39, but doesn't turn it off until 1.41 volts or so. This is important because we want our replacement to have a higher voltage than this when fully charged. Okay, so I know what the current and voltage characteristics of the calipers are. Now I can move on to designing a PCB that can match the output of the battery we're replacing, and by PCB I mean getting nowhere near a printed circuit board. Next, I need to calculate what the equivalent series resistance of the caliper circuit is, which will allow us to simulate that with a load resistor. To do this, I use a spreadsheet and Ohm's law to solve the resistance as an output. So 1.5 volts divided by 15 microamps is 100,000 ohms. Close enough. Next, I use a program called LT-Spice, which is great for tinkering with circuits and learning about the basics of electronics. The program allows you to place virtual probes anywhere on your circuit and see the voltages and waveforms of all the signals. This isn't a training video on this, but there are lots of them online and also lots of other software options out there. I have QSpice, but I haven't done much with it yet. There are powerful programs and they have a bit of a steep learning curve. I would search YouTube if you are interested in learning more. For our circuit, we are going to have a voltage source and that 100k ohm load resistor I calculated earlier. I decided to use a simple 2-transistor setup to create a voltage and current regulation circuit. Bipolar junction transistors of the PNP variety, which are acceptable choices for this application. These are current control devices that can control the flow of a much higher current on the 2 leads with a much smaller current on the 3rd leg. A bit more voltage drop versus some of the other solutions, but we have 5 volts of USB to start with, so losing 0.6 volts across the transistor is no big deal. There are so many ways to do this. This is just the one I picked since I had the parts. This circuit will take a wide input voltage range from our super or ultra capacitor and will output the 1.5 volts needed by the calipers. Back in my calculation, I calculated the estimated dropper resistor for current regulation. Note the low turn-on voltage used. At tiny currents, the BC337 transistor starts to turn on very early. Next, we need to determine the voltage range for the power source, which in this case is a 4 farad 5.5 volt rated supercapacitor I had in my workshop. This is an eBay special, so I don't even have a datasheet for it, but it's a can, it stores charge. These have awful ESR, by the way, fine for super low current circuits like this one. I used the formula shown here to calculate how long the calipers would run with the quiescent current from my caliper circuit plus the actual calipers themselves. Not bad, 4 days or so, which is acceptable for my use case. To calculate how long it will take to charge the circuit, I inputted the variables for the capacitor's data sheet into the simulator. I wanted to be able to charge it from a standard USB power adapter, and I might have a few of those laying around here. Using a 5 volt output, 1 amp power adapter, it looks like 4.7 ohms is the choice, and the charging time is going to be on the order of 1 to 2 minutes from fully flat. That's faster than finding and changing the battery, so that's a win in my book. I chose a resistor that is big enough that even if it shorts out, it can handle the power of the USB adapter. The decision to go with a discrete transistor design started with some work I did years ago. The tiny linear regulators with even low microamp quiescent current tend to drift to higher voltage with very light output loads. I tested several of these over long time periods, years, and I found that most of them ended up near the rail voltage eventually with only a few microamps of load. So having to add a resistor outside the regulator to stabilize the output means that the quiescent current that looks so good just moved outside the component, and in the case of using the supercapacitor, there just isn't enough energy available to support this. So it goes to show that the easy one-chip solution doesn't always work the best. Also, the specialty regulators are expensive. A transistor costs a few cents, a specialty regulator can cost $1 each. Switching converters are out of the question at these power levels. Since this is a very simple circuit, I decided it would be easiest to assemble this dead bug style and skip any kind of circuit board. This means it won't be as pretty or compact as it could be, but it is a great way to make a proof of concept if it only has a few components. Kinda reminds me of old tube circuits, and this is more enjoyable to me than going out and buying a new battery that would go flat in no time. This is where I ran into the issue I alluded to earlier. Building this by hand with small components ended up being pretty finicky and made the build more challenging than anticipated. I would still recommend that even if you are new to circuits to give this a try. It might be a bit frustrating and it will take some time. You get to enjoy this sped up assembly, which in real life took around 20 minutes. Okay, time to juice up the capacitor and test it out. The circuit charges up in a minute or two, which is exactly as expected, and we switch it on and it doesn't work. Low battery warning. The voltage is good, so why is it reading low battery? Remember when I said I made an error when measuring the current draw of the calipers? I only looked at the average current on a multimeter, and that is not the full picture. The calipers read the position of the jaws regularly by using a sensor. I didn't tear them down, it doesn't matter what kind of sensor. The idea is that when the sensor reads the jaw position, it uses a lot more current. That wasn't part of my calculation in simulation, since I just used a resistor as my load, and without any storage on the output, the regulator circuit of any larger current drawing will instantaneously cause the voltage to drop low. The calipers have a low voltage alarm at 1.39 volts, so every time the position is read, the low voltage alarm also trips. So short duration, high current pulses are making the circuit not work correctly. An oscilloscope would have shown this right away. The simulator wasn't set up to have that pulse of extra current on the output, so it shows no difference. Thankfully, there's a ready-made solution to this problem, and we already use one to store the primary energy. The problem is solved by adding a 3.3 microfarad capacitor to the output, shown here in the simulation. This doesn't change the behavior of the circuit in the simulator, but it makes all the difference to the real-world performance. Normally, regulators have an output capacitor. I was just being cheap, and since building this without a circuit board, I wanted as few components as possible. The capacitor will help provide the extra current needed during the high current sensor reading time and prevent the low voltage circuit from tripping. So now that that is added in, I can check if these are working. It looks like the calipers are still measuring, so that's good. Final touches now. Adding the USB connector, the charging resistor, and some heat shrink. Let's plug it into some USB power and see if it charges up. There it is. Looking great. All charged up and ready to go for at least a few days. I can do some final measurements to make sure everything is working okay, and it looks great. I've been using these for several months now, and everything is working great. Pop the USB cable in for a few seconds and you're good to go. Certainly room for improvement on the circuit, but it's working and it's reliable, so that's enough for me. So I accomplished what I set out to do. The calipers are working, and I think this can do with some improvements. First of all, the calipers don't fit in the case anymore, so a solid next step for this is assembling the components a little more carefully and adding a printed circuit board. This wouldn't be bad for powering other low voltage electronics, maybe add a solar cell to top off the supercapacitor. I've had these circuits running for years actually, even indoors. The "it's nighttime" indicator has been going for 10 years. Batteries. Where we're going, we don't need batteries. So I might get organized and put up files online to build something. Never gonna happen. Let me know if you'd be interested in it and I'll get to work. The easy part is done, and now I have working calipers whenever I need them. They charge fast, they work when I need them, and I definitely have enough USB adapters and cables around, so that isn't an issue either. As usual, thank you very much for watching and sticking around to the end of the video. If you really like this one, please hit the subscribe button and give the video thumbs. Next week, I will be doing a buyer's guide and summary video of the power adapters from the last year, along with an overview of my top picks. Thanks again, and goodbye.